It is nowadays becoming quite common to be working with datasets of hundreds or even thousands of features. If the number of features are that substantial or even bigger than the number of observations stored in a dataset, then this can most likely lead towards a machine learning model suffering from overfitting. In order to avoid this type of problem, it is necessary to apply either regularization or dimensionality reduction techniques. And that's where the concept of feature extraction comes into play. Having said that, I welcome you all to this session on feature extraction using R programming language session by Intellipaat. With this session, we are going to cover how you can perform the feature extraction using factor analysis methodology. But before we dive into its technicalities, I'd like to request you guys to enable both the subscribe button and bell icon for our Intellipaat YouTube channel so that you don't miss out any technical update coming from our end. First of all, let's look into the agenda for our session. We'll begin this session on a friendly note where we'll talk about what feature extraction really stands for. After that, we shall understand the theoretical details about factor analysis methodology and when you should put it to use. Finally, we shall get through the hands-on demo where we shall perform feature extraction using factor analysis method and R programming language. I hope I have made myself clear with the agenda. So without wasting any time, let's go ahead and start with the first topic of our agenda, that is, what is feature extraction? We mentioned in the intro itself, the size of data does matter when we talk about the factors such as accuracy, the way model fits to the data itself. To be specific, the number of data values or the rows you have inside your dataset doesn't make that much difference. But what creates the chaos is the number of features you have in your dataset. Your dataset might contain multiple factors that don't really support learning or perceiving of the pattern. For example, suppose you have the sales data that contain the names of the customer, their age, their profession, their salary, bank balance, product they are interested in, and the price of that product, etc. And you are supposed to predict if the given test sample person will buy the product or not. Now, in this particular case, the features such as the name of the customer, their profession, or rather the name of the product they are interested in is not gonna matter much. It's actually going to become extra overhead that model does not require. These kinds of features are termed as noise, and generalizing over them might cause the overfitting instead of helping in better pattern recognition of the data. Remember, overfitting totally depends on the complexity of the model. It happens when the model tries to fit to the noise of the input data and hence becomes too specific that it can't generalize well to new validation or testing data. Any model that is sufficiently complex, for example, one that contains many hidden layers, a large number of neurons in each layer, whose weights are not regularized, can easily converge to give very little loss on training data. But they will definitely result in poor accuracy on test data. In this graph present on screen, you can visualize the scenario of overfitting. The first thing you can visualize is how the model is gaining good accuracy while training, whereas in case of validation or testing, the error becomes mammoth. To give you a real world example, consider that you have been tasked with predicting quality of tennis ball. The feature chosen as color of the ball is irrelevant, but the network will learn from training examples and there is a chance that since people like yellow colored balls to play with, they play more often with them and those balls don't last longer because their use is significant, right? Now, in this case, the yellow ball will be rated worst, which is a wrong prediction considering the amount of time it has been used for. Now, what can we do about this problem of overfitting, or what can we do about too many features, or what we call dimensionality of our dataset in more technical terms? Well, there are two things we could put up as a solution here. First thing is regularization of the data. As mentioned earlier, overfitting occurs when a model learns the noise and random fluctuations in the training data rather than the underlying patterns that generalize well to new data. Regularization achieves this by adding a penalty term to the model's cost function, which controls the complexity of the model. This penalty term discourages the model from fitting the training data too closely and encourages it to generalize well to a new data. Using regularization could certainly help reduce the risk of overfitting, but using feature extraction techniques instead can lead to other types of advantages such as accuracy improvement, overfitting risk reduction, speed up in training, improved data visualization, increase in explainability of our model. Feature extraction actually aims to reduce the number of features in a dataset by creating new set of features from the existing ones and then discarding the original features. These new reduced sets of features should then be able to summarize most of the information contained in the original set of features. In this way, a summarized version of the original features can be created from a combination of the original set. Another commonly used technique to reduce the number of features in a dataset is feature selection. The basic difference between feature selection and feature extraction is that feature selection aims to rank the importance of the existing features of dataset and discard less important ones. Basically, unlike feature extraction, you don't create a new set of features that summarize your original data. In this session, we are going to focus on the feature extraction with the technique of factor analysis. So, since we have covered why high dimensionality is a problem and how feature extraction poses as a solution, it's time for us to go ahead and talk about the factor analysis methodology and its theoretical details. Factor analysis is one of the unsupervised machine learning algorithms which is used for dimensionality reduction. This algorithm creates factors from the variables that are given inside dataset to represent the common variance. What I mean by common variance here is that it is a mere variance due to correlation among the given feature. Yes, it sounds a bit more technical and difficult from this point, but let's break it down into slices so that we could perceive it better. First, let me give you an example. Let's imagine that every one of us is now a recruiter and we want to hire employees for our business firm. The interview process has been over, and for each personality of the interviewee, we have rated them out of 10. The various personalities of the candidate are distant, relaxed, careless, talkative, lazy, and underconfident, etc. There are about 32 variables or features that we have rated candidates on. We can see that relaxed, careless, and lazy features are correlated because these persons won't be successful. Since these variables are correlated, we can try to form a factor called as unsuccessful behaviors, which will explain the common variance, that is, variance due to correlation among these features such as relaxed, careless, and lazy. Similar to this example, the correlated variables in your dataset can be merged together on the basis of common variance. Mathematically, common variance is represented as x minus mu is equal to L f till n plus epsilon. X is the number of features or dimensionality and f is the factor. And L is the factor loading, which can also be considered as the weight of the factor for the corresponding variable. The number of factors is equal to the number of features you have in your dataset, and we are going to remove mu features or variables out of those x total features. I hope this equation makes sense. Let's talk about the approach we are going to put to use to achieve the mathematical results that we just discussed. Basically, to do factor analysis, we are going to perform various steps such as Bartlett's test of sphericity, KMO test, determining the number of factors, and interpreting the factors. Also, before doing this, you'll need to make sure that you have removed the outliers, standard scale the data, and also the features that you are working on have just numeric values. Now, first, let's talk about the Bartlett's test of sphericity. Bartlett's test checks whether the correlation is present in the given data. It tests the null hypothesis that the correlation matrix is an identical matrix. The identical matrix is basically the one which consists of all the diagonal elements as one. So the null hypothesis assumes that no correlation is present among the variables. We want to reject this null hypothesis because factor analysis aims at explaining the common variance, that is, the common variation due to the correlation among the variables. If the p-test statistic value is less than 0.05, we can decide that the correlation is not an identical matrix. That is, correlation is present among the variables with 95% confidence level. If this condition holds true, that is p-test statistic value is less than 0.05, we can go ahead and apply the factor analysis method. Now the next step we have is KMO test, which is an acronym for Kaiser-Meyer-Olkin test. KMO test measures the proportion of variance that might be a common variance among the variables. Larger proportions are expected as it represents more correlation is present among the variables, thereby giving way for the application of dimensionality reduction techniques such as factor analysis. KMO score is always between 0 to 1 and values more than zero point 0.6 are much appreciated. We can also say it as a measure of how suited our data is for factor analysis. Now, the third step we have is determining the number of factors. The number of factors in our dataset in the beginning is equal to the number of variables in our dataset. And we know that all the factors are not going to provide a significant amount of useful information about the common variance among the variables or features. So we have to decide the number of factors. The number of factors can be decided on the basis of the amount of covariance factors explain. In general, what we do is we plot the factors and their eigenvalues. Another way is to perform the scree test. To talk about eigenvalues, they are nothing but the amount of variance the factor explains. We'll select the number of factors whose eigenvalues are greater than 1. But why should we choose the factors whose eigenvalues are greater than 1? The answer is very simple. In a standard normal distribution with mean 0 and standard deviation 1, the variance will be 1 as well. And since we have standard scale the data, the variance of a feature is going to be 1. This is the reason for selecting factors whose eigenvalues or variance, let's say, are greater than 1. That is, the factors which explain more variance than a single observed variable. Now, the final step is interpreting these factors. Once you have an optimal number of factors, then we have to interpret the factors by making use of loadings, variance, and commonalities. Loadings indicate how much a factor explains a variable. The loading score will range from -1 to 1. Values close to -1 or 1 will indicate that the factor has an influence on these variables or features, whereas values close to 0 indicates that the factor has a lower influence on the feature. Next is variance. Check out the screenshot over here. The first row represents the variance explained by each factor. Proportional variance is the variance explained by a factor out of the total variance. And cumulative variance is nothing but the cumulative sum of proportional variances of each factor. In our case, the three factors together are able to explain 56.8% of our total variance, which is a good number. In unrotated cases, the variance would be equal to the eigenvalues. Rotation changes the distribution of proportional variance, but the cumulative variance will remain the same. Oblique rotations allow correlation between the factors, while the orthogonal rotations keep the factors uncorrelated. Then we have communalities. Communality is the proportion of each variable's variance that can be explained by the factors. Rotations don't have any influence over the communality of the variables. The proportion of each variable's variance that is explained by the factors can be inferred from the above. For example, you can see that for this variable or feature talkative, we are getting 62% of variance coverage, which is a very good number to work with. Even after knowing all these theoretical details, things might be quite blurry for you. So let's go ahead and get our hands dirty by doing factor analysis on a real-time dataset. The dataset that we have here contains 10 columns or what we have been calling features all this time. And it has about 1000 rows of data entries. Basically, It is the dataset of customer rating on the scale of 10 for features such as performance, leader, latest technology, fun interior, serious interior, bargain allowance, value for money, trendy products, and would you rebuy from the brand. Also, at the end, it contains a column which contains the name of the brand. I hope the dataset details are clear to all of you guys. Now let's go ahead into the R Studio and get this dataset loaded. The function that we use for reading and loading the dataset into R file is read.csv. And inside this function, what we'll do is we'll pass the location of our file where it is stored. So for that purpose, let's first get this read.csv function ready, and inside parenthesis we'll pass the location. However, let's first gauge the location of our dataset file. So here we have our customer rating dataset file, and this is the location path for this file. So we'll copy it, we'll paste it here, and as we know in R, the location path shall be represented with double slashes. So we'll represent it with double slash, and then we'll add the name of our file, that is customer underscore rate dot csv, and let's run this line. And here you can see that the dataset has been loaded into our console. So next, let us print some details about our dataset. First, we'll highlight the dimension of our dataset with the function named as dem, and after that we'll also print the 10 initial records of our rating dataset. Alright, so let's run these two lines of code, and here you can see that we have 10 features and the 1000 rows. Alright, and the first few entries in our dataset are highlighted over here as well. So now moving ahead, we shall scale our data with the help of a standard scalar transformer in our programming language. In order to do that, first of all, let's create a copy of the rating data frame. So we'll name this copy as rating.sc because it will be the standard scaled version of our data frame, and we'll actually paste all the records of rating data frame. Now what we'll do is we'll perform the standard scaling. So for that purpose, we'll use the scale function, and inside scale we'll pass the numeric columns that we have in our dataset, that is number 1 to number 9. We won't be passing the brand column because it contains the categorical data, and as we mentioned earlier through the PPT part, that we can only pass numeric data to this type of algorithm. So particularly what we'll do is we'll pass column 1 to 9 to this scaling function, and we'll store these results inside rating.sc data frame. Now let's run this code. Next, let us print the head of this rating.sc data frame, as well as let's print the summary statistics for it as well. And after running, you can see that the mean has been dropped to 0 over here. So basically what scaling function does is it center the values around mean and scale them to have a standard deviation of 1. Basically it will convert our data into the normal distribution or Z distribution. Okay, now moving forward, we shall perform the correlation analysis on the standardized ratings data. First, we'll have to load the psych library because it has the core.test function which produces this correlation table that we want.
Alright, so first of all, let's load this psych library and let's run this line. Next, we shall use the core.test function and pass our data through it. So for that purpose, we'll call this core.test function over here, and actually we can only pass the matrix data inside this core.test function because it only transforms the matrix data, and right now the rating.sc is in data frame format. So first of all, we'll have to convert it into the matrix format, and for that purpose we are going to use adds.matrix function, and inside it we are going to pass the numeric data part of our scaled rating data frame. Alright, that is column 1 to 9. Now let's run this line of code. So after running that command, we have got the correlation matrix over here. And from this correlation matrix, we can see that there are some values greater than 0.5. For example, leader has 0.5 plus collinearity with the perform column. And similarly, serious column has 57% collinearity relationship with the leader column. Same goes for trendy with latest, and many more columns inside our correlation matrix. That means the features in our dataset are correlated to each other for some extent. Now, what that suggests is there is high collinearity and correlation between our features. So, moving ahead, what we shall do is we shall estimate the number of factors by using the scree test and eigenvalues test that can represent the whole dataset within the minimum number of factors. All right. So for that purpose, what we are going to do is we are going to load n factors library. So n factors library is necessary to calculate the factors that we are talking about, and it will have both scree test as well as the eigenvalue test inside it. So first of all, let's load this library n factor. Now let's run this line. Now next, we shall use the scree method to contemplate the number of factors. Basically, this scree method has 4 different methodologies that determine the factor values for you. All of them differ from each other, so there is probability that you might get different results. So in those cases, what you should do is you should take the mean value of those results as your factor value. Now let me show you guys how the scree table is. So I'll use the function nscree and will pass the rating.sc data frame through it. So let's load that function over here, nscree, and we'll pass the numerical part of our scaled rating data. So it will be again column 1 to 9. Now let's run this line of code, and after the scree test you can see that maximum methodology is saying that 3 should be the number of factor, and Kasa is saying 3 should be the number of factor, and parallel methodology is again saying that 3 should be the number of factors. NOC is again saying the number of factors should be 3, whereas NF is saying the number of factors should be 2. As discussed earlier, the different methodologies could yield into different results. However, the result we take will be considered dependent on the maximum number of value all other methodologies suggest. Alright, so since here we have 3 votes for 3 as a factor value, so we'll say that 3 is the right factor value. However, we'll also perform the eigenvalue test to find out the number of factors. Basically, eigenvalue test is used to calculate eigenvalues and eigenvectors of the correlation matrix of given data. This is a necessary step in performing a factor analysis. So let's go ahead and perform this eigenvalue test as well. Here we'll use this eigen function, and inside it we'll pass our rating data but actually we are supposed to provide the correlation matrix. So for that purpose, we'll use core function, and inside it we'll pass the rating data. Now let's run this line of code again. And here you can see that we have got eigenvector values as well as eigenvalues. So here you can see that it is again yielding around 2.97, which is again very close to 3. So let's decide and manifest that 3 is the ideal factor value for our data. Now moving forward, we shall perform the factor rotation. So basically factor rotation in R refers to the process of transforming the factor loadings in a factor analysis to a new coordinate system in order to simplify the interpretation of the factors. The rotation is applied to the factor loadings to produce a set of new orthogonal or oblique factor loadings that have the same explanatory power as the original factor loadings. So guys, basically as discussed earlier in the PPT part, the loadings are basically can be considered as weights for our model. Alright. So basically these are the factors that we are going to train. So here these orthogonal and oblique rotations are going to allow us more explanatory power for explaining the covariance. So that is the reason why this step is quite crucial in our feature extraction journey using factor analysis. Now, there are several methods of factor rotation available in R, including Varimax, Oblimin, Promax, and many other. The choice of rotation method depends on the question, the data, and the assumption about the underlying factor structure. Orthogonal rotations, such as Varimax, produce uncorrelated factors, meaning that each factor is independent of the others. This is useful when the factors are expected to be unrelated. Oblique rotations, such as Oblimin and Promax, produce correlated factors. That means when we have correlation in our dataset, then we shall go for Oblimin or Promax rotation. So these oblique rotations are going to allow the correlation among factors as well. Now this is useful when the factors are expected to be related to each other, which is true for our case, alright. Now the GPA rotation package in R provides the range of factor rotation methods including Verimax, Oblimin, Promax and many other. These methods can be specified in the rotation argument of the factanal function. So first of all, what we are going to need is we are going to need to load this GPA rotation library and perform the factor rotation. So first of all, let's load this library into our R file, library GPA rotation, and this library contains the factanal function which we are going to use for the rotation purpose. And the output of this factanal function will include the rotated factor loadings as well as other information such as communalities, proportion of variance, explain and goodness of fit statistics. So first of all, we shall load this factanal function and apply it to our dataset. Factanal rating.sc numeric part. Then we have found out that the factor values we had was 3. So it's an argument for this factor function equal to 3 and the type of rotation that we want to use. First of all, let's set the rotation as Oblimin. Now let's run this line of code. Guys, here you can see that there is one mistake in the name of object, that is the name of our data frame. So we'll have to correct it and rerun this line again. Now after rerunning this line, you can find that all the three factors together lead for 55% variance of our data. and you can see that the overall variance covered by three factors for all of the nine factors is about 55%, which is quite a good number, isn't it? Besides, you can note that features such as bargain, value, then leader, latest are covered for more than 80% of their variance. Now, next, let's perform the order rotation method, that is Varimax, which is again the orthogonal rotation method. So we'll copy the above line and we'll paste it over here, and we'll change the rotation method name to Varimax. Now let's run this line of code, and here you can see that with Varimax we are getting 56.8% total variance coverage with these three factors. Alright, and the factors such as bargain, value, then latest have been covered for almost 80% of their variance by these three factors itself. Alright, so again, the one thing to note here is we are getting 56% of variance coverage. What that means is, meanwhile, we are also losing on 44% information by excluding 6 columns and just converting 9 columns to the 3 columns, alright? But that gives a rise to new question. That is it okay to lose 44% or 45% information from the data? I mean, a common rule of thumb for determining the amount of information retained in a factor analysis is to retain factors that explain at least 60 to 70% of the total variance. However, this threshold can vary depending on the nature of data. Now, in our case, currently we are around 56 or 55% of variance cover. So let's try yet another rotation method, and let's see if we could increase it to 60%. The rule of thumb that we discussed earlier. So basically, our target is to get 60 to 70% variance coverage for overall of our data. All right. Now, to do that, what we'll do is we'll again copy this fact anal statement and we'll paste it over here, and now we'll use Promax rotation. Let's run this line of code, and here you can see that the Promax is leading to almost 59.5% of variance covering. What that means is we have reached that 60% threshold, right? I mean, 59.5 is close enough to 60%. That means we can use these factors to proceed forward and yield the results or predictions that we want. So basically, we have managed to boil down these nine different features to just three features, and that is how the feature extraction, or what we call as the method of factor analysis, works. I hope the theory and coding implementation of feature extraction using factor analysis is clear to all of you guys out there. That's all we have for the session today. I hope the concept covered through this session is clear to all of you guys out there. If you have liked the concept covered through this session, make sure to hit that like button and subscribe button to Intellipaat YouTube channel. Until next time, goodbye.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.